phi. So it is not necessary. We can pass to the definition of the limit. No questions with as for the quantifiers.
No, I don't have any questions about that.
Okay, so page number 6. I think it's the definition of the limit. Can you see page number 6?
Yes, I can see it.
Okay, so I hope that you know this definition from your lectures, but we have to recall this. So what is the limit? We say that a sequence x sub n has a limit p. In this case, if you like any other letter, you can take A, B, C, D, and other letters. Z. For any positive epsilon, we can find a natural number, capital K, depending on this epsilon, such that the absolute value of x sub n minus p is less than epsilon whenever the index n is greater than k. And using the quantifiers, we can say that you see the formula 2.1. For any epsilon, there exists k of epsilon, which is a natural number, such that for all n greater than k of epsilon, we have that the absolute value of xn minus p is less than epsilon. You see here, we have, it is not a problem. In fact, it is some problem of notation. You see, in fact, here I write, as in the Russian literature, that the number capital K depending on epsilon is a natural number. It is logical because in our sequences we are dealing with some terms with the index which is a natural number. But in fact, you have to know that in this definition we can say that k, capital K, of epsilon, in fact, it can be a positive but real number. But in the Russian literature, we use the notation for this capital K as a natural number. So we try to find always a natural number k over epsilon such that. Is it clear, this remark?
Yes, it's clear because we've seen it in a lecture, so we were able to go over it before.
So either natural number or real number, but positive. But for every epsilon we have, you see, as for the quantifiers, as as it was remarked before, for any there exists. So I take epsilon, then I can find if the limit exists. I can find such k. Okay, I hope that it is clear. So as for the sentences, using the word limit, we say you can turn the page, and the standard notation is limit as n goes to infinity of xn is p. Then this means you see the word limit is clear. N goes to plus infinity. Really, usually we write only n goes to or n tends to infinity without plus, knowing that we are dealing with the natural numbers. We can also write, you see the second line, the second formula, xn tends to p as n tends to infinity. And you can also write that xn goes to p without writing that n goes to infinity, because there is no problem with notation. There is no another way, if you want, to say that the limit of this sequence is p. I hope this notation is clear. Good. So page number 8. There is an exercise number 2. Can you see this exercise?
Yes.
So the first example, a simple example of a limit which has, or of a sequence which has a limit. So we said that x sub n is n over n plus 1. The first, you see, in this exercise, we say that this sequence seems to have the limit p equals 1. But the idea of this exercise is to use the definition of the limit using the fact that we hope or we know that the limit is 1. So in some way we know that the limit is 1. So using the definition, we have to prove this result. So we turn the page and we try to show, to underline that 1 is really the limit of this sequence. So the hypothesis, it is not mathematics, it is only our observation. So if I take n equals 10, I can calculate my term x sub n, it will be something written here. If I take n 100, then I will have another term which approaches 1. And if I take n 1000, I will have that x sub n is something like 0.999 and so on. You see, our idea about the limit of this sequence is rather good, because if I take n 10,000, you will see that xn will be rather near 1. But this is only an idea. Now we will try to use the definition of the limit. So we take epsilon positive. If you want, we fix this epsilon, and now we have to find the corresponding, we will say, a cut-off number, capital K, which depends on epsilon, such that x n minus p, that is in our notation n over n plus 1 minus 1 is less than epsilon whenever n is greater than k, capital K. Is it clear for the moment that here we use only the definition of the limit, and we replace x sub n by our sequence p with our limit, and here we have epsilon, and we want to find this cut-off number k of epsilon. Is it clear?
Yes, so far it is.
No problem. So, as for the left-hand side of this inequality, so using a common denominator, we have that our inequality reduces to the inequality, the absolute value of minus 1 over n plus 1 is less than epsilon, or exactly 1 over n plus 1 is less than epsilon. So here, for the moment, we do not know this cut-off number, capital K of epsilon. We do not know. But from this inequality, the last one, 1 over n plus 1 less than epsilon, we can see that in this case, 1 over epsilon is less than n plus 1. Is it clear how to obtain this inequality?
Yes, it's clear. I understand how to get it.
Good. Well, so we have to find our cutoff number, capital K, from this inequality. N plus 1 is greater than 1 over epsilon. So if we turn the page, we can see that this inequality is equivalent to the inequality n is greater than 1 over epsilon minus 1. So you see that here we have a difference, because if I say that my cutoff k of epsilon is a real value, so I can take k as 1 over epsilon minus 1, because it is a real value, and for all n greater than this k, I will obtain my initial inequality. Is it clear?
Yes, it is.
But a little trick here. I want to find a natural cutoff k. You see? So I will take k as an integer part of 1 over epsilon. So I don't know. You know the term, this function integer part.
Which word again?
The integer part of some real value. In this case, the positive value. The integer part.
No, I don't know what to do.
So here, I write k is integer part of 1 over epsilon. And I write where integer part of x is the greatest integer less than or equal to x. So, for example, the integer part of 2.53 is 2. The integer part of 3.15 is 3. You see? So if I divide 1 over epsilon, I will obtain some real number. So the integer part plus something after point. I don't know, 100.55. So the integer part will be 100. Is clear. I
Yes,
speak
clear.
only about the positive numbers. It is not necessary to discuss the negative numbers. There is another definition, but now we are dealing only with positive numbers. So if I write that it will be 1 over the integer part of 1 over epsilon, my k, then you see I can see that if n is greater than the integer part of 1 over epsilon, then it will be greater than 1 over epsilon minus 1. And for this k, cutoff k, we have our desired inequality. N over n plus 1 minus 1 is less than epsilon. Is it clear?
Yes.
Onya, is clear?
Yes. Yes.
Eric, is it clear?
Yes, sir, it is.
So you see here there is an example. If I take, for example, epsilon as 0.002, then it is not very difficult to find that your cutoff K is 499. Then if we start from the term with the number 500, then we will have that the difference between our x sub n and 1 will be less than epsilon. You see, if I take a remark, if I take the integer part of, for example, of 2, it will be 2. If I take an integer part of 3, it will be 3. If I take an integer part of 100, it will be 100. You see, in this case, with this special choice of epsilon, we have no problems with the integer part of the value 1 over epsilon. Clear?
Yes, it's clear.
Good. Now. So the next exercise is, the idea of the next exercise is the same. It is the idea of this cutoff number, So we take the sequence X, it's page 11. So we take a sequence X sub n, which is 1 over square root of n. And we hope that the limit of the sequence is 0. And we want to find a cutoff number, capital K, which ensures the inequality xn minus 0, the absolute value of this difference is less than 1 over 30. So if we turn the page, we see that in fact, if you write the absolute value of x sub n minus 0, it will be 1 over square root of n. So our inequality, which we use in order to have our cutoff number, will be 1 over square root of n less than 1 over 30. Then we see that we can solve this inequality in order to have that n is greater 169. I hope it's clear.
Yeah, it's clear.
It's clear. So in this case, the cutoff number, capital K, is 169. If we want, it's the end of this exercise. If I want to have the difference of the absolute value of the difference x sub n and 0 less than 1 over 100, then I can see that n is greater than 100 to the second power, or 10,000. So this cutoff K will give a desired estimate between the nth term of our sequence and the limit. Is it clear?
Yes, it's clear.
Clear. Well, now we will start something, because you know, if I take the definition, maybe it is a hard work in some cases, but if we know first of all some limits, some classical limits, and also we will know next Friday, I hope, if we will know some limit theorems, we can use these results to calculate our limit. Because you see, with this notation, epsilon k of epsilon, it is not useful to calculate limit, especially for the researchers. But if we know something, then we can use these auxiliary results to calculate these limits. So we start with some classical results, with some classical limits. So page 13, we have exercise number 4, and here we have two statements. So first of all, if I have a constant sequence, that is x sub n is a for any n, for any natural n, then if I try to use my definition of the limit, I can take the cutoff capital K, which is 1, and if my sequence is constant, so x sub n minus a is a minus a, so it is 0 for any epsilon positive, for any positive epsilon. So due to the definition of the limit, we have that the limit of a constant sequence xn equals a is a. I hope it's clear.
Yes, it's
No
everything's
problem.
clear.
No problems. Then, if I take the second statement, if I take alpha, a real number, and alpha is strictly positive, a real number, then I have that the limit of a sequence 1 over n to the power alpha is 0. So it is the second important limit which we have to remember. How to prove this result? You turn the page 14. So we take some positive epsilon. Then if I take any alpha, a real alpha, then I can always find some beta, a rational number, such that beta is less than alpha. So you see, I will not comment this statement. You have to know this from your lecture. But for example, if you take the number, the real number pi, you know, it is 3.14 and something else. You see, if I take my beta, if alpha is pi, and if I take beta 3.14 and nothing else, then 3.14 is a rational number which is less than alpha. So in this case, my inequality is valid. Is it clear?
Yeah, it's clear.
Clear. Clear. Clearly. So
Yeah, I understood it. Everything was clear for me, but I'm not sure if everybody understood it. So we can ask.
Onya, it's clear. Thank you. Good. So. Then you see we have that n is greater than 1. And with my beta, which is less than alpha, I have that 1 over n to the power alpha is less than or equals n, oh, pardon, 1 over n to the power beta. Is it clear?
Yes, clear.
Clear. You see, with the powers of this type, beta and alpha, we have 3.3. So here, you see, it's an important point because we are looking for our cutoff k, in fact, for the sequence 1 over n to the power alpha. But if I take that 1 over n to the power beta is less than epsilon, so the equation 3.4, you see, then in fact I will have that 1 over n to the power alpha is also less than epsilon. Agree?
Yes.
So
I
you
agree.
see in what is important here. I say in the definition of the limit, for any epsilon, I can find a cutoff capital K of epsilon. We can say that if this inequality x sub n minus the limit absolute value of is less than epsilon, beginning from, for example, the term with the number 100, or if this inequality is valid beginning from the number 150, there is no problem because for this epsilon, we have such a number. You see, it is not important the exact value of this k. The important point is the existence of this k. You see? So, in fact, from this inequality 3.4, I can find my cutoff value 1 over epsilon to the power 1 over beta, or the entire part of this value plus 1. So if I take, for example, you see here I present you the solution of the inequality 3.4. But if I add to this and to this entire part, integer part 2 or 3 or 4, it will be the same result. It will be the same result. So if we take such a K, such a capital K, we will obtain our desired inequality, that 1, the absolute value of 1 over n to the power alpha minus 0 is less than epsilon. Is it clear or not?
It's
Yeah.
Clear? Really? Clear?
Yes.
Yeah.
Oh, good. So now, the next limit, which is important for us, you turn your page, and here we have exercise number 5. So if I have some real a, which is positive, which is strictly positive, then the limit as n tends to infinity of nth root of a is 1. How to prove this statement? First of all, if a is 1, then evidently this statement 3.5 is evident. Is it clear for you? Because nth root of 1 is 1, so we have a constant sequence 1, 1, 1, so on. And the limit of a constant sequence in this case is 1. Clear?
Yes, it's clear.
Very good. Now the second situation. If I take a strictly greater than 1, then evidently the nth root of a is greater than 1. Now we use Bernoulli's inequality. I hope that you remember this inequality, but if not, we will see this inequality in the next line. So I represent, you see, a as 1 plus the brackets nth root of a minus 1 to the power n. This is it clear for you, this representation?
we apply the Bernoulli's inequality in
Stop,
this
stop,
case.
stop.
Yeah?
Now, for the moment, the first step, you see, I represent my A like this. A equals 1 plus something to the power n. This step, is it clear?
Yeah, it's clear.
Clear. Really?
Yes.
No problem. So now, I want to use this Bernoulli inequality. So please check this inequality in the seminar number 2 or 1, maybe 1. So here you have 1 plus, I don't know, 1 plus x to the power n. Then by this inequality, we have that it is greater than 1 plus this x multiplied by n. In our case, this x is nth root of a minus 1. It's a positive number. It's a positive number. So I have, by Monsieur Bernoulli, I have this inequality. Is it clear?
Mm-hmm. Yes.
Yes. Good. Good. So you see, if I add 1, which is a positive number, to something which is also positive, so 1 plus nth root of a minus 1 times n, then it will be greater than nth root of a minus 1 multiplied by n. I hope it's clear. This inequality is stronger.
Yeah, it seems clear.
Clear. Well, so from this inequality, you have the left-hand side of this inequality. A is greater than nth root of a minus 1 times n. Yes? Now, from this inequality, I have, you see, nth root of a minus 1 is less than a over n. So, you see, for the moment, I think that you do not know the theorem of two policemen, the squeeze theorem. Do you know this theorem? Eric, you know this theorem of two policemen or squeeze theorem?
I think in the lecture we looked, but
So,
it's something like that in the middle, if we have a limit in the right and in the left.
yes,
In the middle.
very good. But for the moment, you see, it is good to know this theorem because our life is better. But for the moment, I can say that the end of this proof we can do as in the previous example. You see, In the previous example, we had 1 over n to the power alpha is less than 1 over n to the power beta. And then we are dealing with this 1 over n to the power beta. This is exactly the same thing. But here we are dealing with the sequence a over n. So from this inequality, I take that a over n is less than epsilon. I can find my cutoff k depending on epsilon, and this cutoff works for my sequence nth root of a minus 1. This means that the limit of this sequence nth root of a is exactly 1. Is it clear?
Yeah, it's clear.
Clear? Thank you.
Yes,
Clear, really. No problem.
no problem with
So for the moment, we do not use the theorem of two policemen, but we use only our knowledge from the previous exercise. You see? So we can complete our proof by the same arguments as in the previous exercise. You have to think about at home, I hope, I think, I propose you. So you will have this result 3.5. Agree? Now, this result 3.5, here for the second step, we suppose that a is greater than 1. But if a is less than 1, so it will be the same result, but how to prove it? I will take a quantity 1 over a. If a is less than 1, then 1 over a is greater than 1. I hope it's clear.
Yes, it's clear.
Yes, clear. So from the previous case, we can say that the nth root of 1 over a tends to 1 as n goes to infinity. Now, you see, in this proof, I use something which was not introduced for the moment. It is the so-called limit theorem, and we will see it next Friday, I hope. So we use the following method. If a is less than 1, I write that the limit as n goes to infinity of the nth root of a is the same thing as the limit as n goes to infinity of 1 over the nth root of 1 over a. It is clear. Now, I use this limit theorem, which says it's for you, not for the moment, it's only for you. If I have two sequences, xn over yn, and xn goes to some limit a and yn goes to some limit b, then the limit of the sequence will be a over b. In this case, in the numerator of my fraction, I have a constant sequence, 1. And the limit of the denominator, I know due to the second step of my proof. Then the result will be 1. So, in this case, is it clear how we can prove this third step? I think that you have to know the limit theorems, but I will introduce this theorem later. Is it clear?
I think.
You think?
Yeah.
So I will formulate this theorem later. And if you want, we can return to this case, but I hope that after formulating the correspondence theorem, you will understand without problems this result. Good?
Yeah, it's great.
Bon. So, example for today, we also have the following result, the following limit to remember. So exercise number 6, exercise number 6. Here we claim the following. So if I have some q, a real number, moreover, we know that the absolute value of q is less than 1, then the limit of the sequence q to the power n is 0. You can imagine this result if you take your calculator and you take q equals 1/2. You will see that the limit of the sequence is exactly 0. Calculating the terms of this sequence for different n, 100, 1000, 10,000, you will see that it's really 0. But how to prove this result in a rigorous mathematical way? So the first step, if I take q equals 0, then you have a constant sequence 0, 0, 0, 0, and evidently the limit is 0. So now the second case, we suppose that the absolute value of q is between 0 and 1. So now we take epsilon positive, we fix this epsilon, and we use the Bernoulli inequality. So in this case, you see, I take 1 over absolute value of q to the power n. Because why we take the absolute value of q? Because we can take the sequence, for example, minus 1 over 2 to the power n. You see, the limit of this sequence will be also 0. but we have some a part of my terms which are negative and another part which are positive. So we have to take the absolute value of q. So 1 over absolute value of q to the power n can be represented in the following way. 1 plus 1 over absolute value of q minus 1 to the power n. Agree?
Yes, agree.
Agree. Very good. So, Bernoulli, Monsieur Bernoulli, we have from this inequality that these square brackets to the power n greater than 1 plus 1 over absolute value of q minus 1 multiplied by n. Agree?
Yes.
Yes, it's clear. Then we can forget about 1, and this sum is greater than 1 over absolute value of q minus 1 times n. Clear, as in the previous example.
Yeah.
Yes. So now you see you have the inequality 1 over absolute value of q to the power n is greater than 1 over absolute value of q minus 1 times n. From this inequality, I have that the absolute value of q to the power n is less than absolute value of q divided by 1 minus absolute value of q multiplied by n. Is it clear? It is the simplification of
Yeah.
the inequality, nothing else. So common denominator if you want, but I hope that it is clear for you. So you see that the absolute value of q to the power n, if I take this inequality, is less than epsilon. Then from the inequality, absolute value of q divided by 1 minus absolute value of q multiplied by n, I can find the cutoff number k of epsilon, and I write it in the following way. So the integer part of the corresponding value plus 1. So for any epsilon, we can find some cutoff k of epsilon such that the difference between your q sub n and 0 is less than epsilon. Is less than epsilon. Is it clear?
It is clear.
Really?
Yes.
Yes?
Yes.
Good. So it will be enough for today. See you on Friday, and we will continue with the limits to remember, and then we will formulate this limit theorem, and then we start to to find the usual limits which are necessary for your examination, I hope. Thank you very much.
Thank you, teacher.
Have a good evening.
The same for you.
Thank you. Ciao, ciao.